Hi guys, so welcome to my channel. In this video, I'm going to go through this Leetcode 77A, swim in rising water. And this is a hard problem, but I don't think this is that hard of a problem. I think this is pretty good for practice. This question was asked by Facebook in the past 6 months. So let's dive in. You are given an n by n integer matrix grid where each value, grid at I row and j column, represent a elevation at that point. The rain starts to fall, and at time t, the depth of the water everywhere is t. You can swim from a square to another four directionally adjacent square if and only if the elevation of both squares individually are at, are at most t. You can swim infinite distance in zero time. Of course, you must stay within the boundary of the grid during your swimming. Return the least amount of time until you can reach the bottom right square, which is the coordinate n-1 and n-1. If you start at the top left corner at 0 and 0 coordinate. This is a bit wordy. Let me show you a graph and you understand what's going on. So let's look at this diagram. There are, let's say, the one on the left is one tank, another one is on the right is another tank, and they have a different depth, right? So the number indicate the depth, right? So this one has a 1 unit of depth, and this one has 2 units, and there's a rainfall from the sky, and for 1 unit of time, it will fill up 1 unit of the depth. So for example, if the rain falls for 1 unit, this tank will fill up, and then if there is a person swimming in this tank, and that after 1 unit of time, and this person will at the top of the tank. However, this one is a lot deeper. That's why it takes 2 units of time to stay at the top. So so based on this graph, I apologize for my drawing, which is not that great, but I hope that you get a sense of what's going on in here. So in order for a person to swim from this tank to this tank, it takes in total 2 units of time, because it takes 2 units of time to fill up this tank. So as you can see, to generalize this, will be take the maximum of these 2 tanks if one person want to swim from one tank to another one. So, and this number is 1 and 2. They are the numbers shown on the grid that you saw on the question. Let's jump back. Let's carry on from this problem. And so as you can see, there's an example in here: 0, 1, 2, 3, and it takes 3 units of time to swim from the top left to the bottom right. So let's look at the explanation. So at time 0, you are at grid 0, 0, which is this location, and you cannot swim anywhere until else, because 4 directionally adjacent neighbor have a higher elevation at time 0, and you cannot reach to 1, 1 until at time 3. So with the depth of the water is 3, you can swim anywhere inside the grid, right? Because, and again, so when the time is 3, so this tank is filled, and this tank is filled as well, right? And also is this one, which takes the longest time to fill among all the tanks. Okay, and imagine this is all the cost that you have to pay in order to get to the bottom right? So because the problem right now is to return the least amount of time. That's why this is a cost minimization problem, right? So I would look at this number as a cost, and my goal is to minimize the cost when I traverse from the top left to the bottom right. Let's look at another one. This one over here. So the grid looks like this, and one of the path, and then that has the minimum cost will be go from here 1, 2, 3, 4, and 5, 16, 15, 14, 13, 12, all the way to 11, 10, 9, 8, 7, 6. As you can see, we do not go from here and then go down, right? Because this one is very costly, right? It takes 24 units of time, and we have to wait that long until this tank is filled, and then we can cross over, and then we take the shorter path. I mean, not the shorter path. Actually, it's a longer path, but it's less costly to go from the left to the right, and then go down. However, when we are at the 16, we don't go down again because this again is very costly. So we go to the left and then go down, right? And as you can see, for this path, we don't necessarily, again, as I said, if we don't necessarily go to the shortest one, we go to the one that's cheapest for cost. So one way to solve this is use the heap, right? Because we can pop off the adjacent node that is less costly. So heap, heap might be one of the candidates that can be used for solving this problem. Let's dive in. So let me zoom in a little bit so you can see. We first have a NR and NC. So as you can see, the code is not that bad actually. It's just how many lines? In total, it's 17 lines. Lines. So we first have a NR and NC to keep track of the number of rows and coordinate row and column numbers, and then I have a my heap. The first element that in the heap will be the number that at the 0 and 0 coordinate. That's our starting point, right? The top left, top left coordinate, and then we have a oh, by the way, before I move on, pay closer attention to this heap, the structure of it, right? So basically, it has a 3 elements, okay? And the first element is the number on that grid. Basically, this is the cost I was talking about, right? So the grid at 0 and 0, and the second element is the coordinate, x and y coordinate, right? And the reason why I put it in the front because when this is the target we want to minimize, right? So when the mean heap pop it off, this is the value that is based off, right? So that's why I put it as first element. Okay, now we can move on after we understand the heap structure. We have directions, all right? So we can go for adjacent directions, and this is why we need that. The max cost, I initialize as a 0 value, and I have a scene set to keep track of all the coordinate that we are seeing along the way, so we don't repeat the work. And while there's something in the heap, and we pop it off from my heap that I initialized before, and pop off as a temp cost, and also temporary row coordinate and a temporary column coordinate. And when we move to the next coordinate, we have to always pay the maximum between the current cost and the next cost, right? And this is connects to what I discussed before. Let me jump back to that paper that I had before. Remember in this graphic, for example, on the one on the left is 1, for the one on the right is 2, and then the cost we have to pay is 2, which is the maximum between 1 and 2. Because we have to wait 2 units of time to allow us to swim from the one tank to another one. That's why we have to use the max function. Okay, now carry on. So this is the exit condition, right? So if we are at the top, at bottom right corner, and we are done, so we just return the max cost that we keep track of. And here, this basic is a template. Basically, this is a classic template for a DFS, right? And for the DR, the directions along the row and the directions along the columns in the directions set that we initialized before. So this is the 4 adjacent directions that we can go. And for next row coordinate and next column coordinate, so we have the current position plus the DR, and also the current, and also plus the DC, if that is within the boundary of the grid. And the next one has not been seen before, and we just push it to the heap, and along with the cost we have to pay, right? Because this is when we pop it off in the next iteration, we pop off the one that has the least amount of cost. Again, this is the reason why we use the min heap. And at the same time, we are seeing it right now. So we add it to the scene set, and the loop repeat until the heap exhausted. Let's run it, and it works, and it's pretty efficient as well. So for time complexity, is big over n squared times log n. So basically, this push and also the heap pop and takes a big over n before n time to perform these operations. And there are total n by n number of spots on the grid. That's why it takes n squared times log n. And space complexity entirely comes from the heap. Also, a little bit comes from scene set as well, but the two combined is still n squared. And this is my solution. I hope it's helpful, and thank you for watching. See you next one. Bye-bye.